Hi, my name is Jia Chen, and the topics of today's poster is a transformation-based framework for KNN similarity search. And this is outline. We will first introduce what is a KNN similarity search, and then it's about its related work. Also, we will propose some methods with actual optimizations. And finally, it's about the evolution. So at the very beginning, we will ask a question: what is KNN similarity search? Actually, we can just consider it as a function whose input is a collection of records, a query, and the similarity function. Here, we just use JCOD. And the output seems very complex, but actually it just returns the top K results with the largest JCOD similarity to query. Also, we can say the smallest JCOD distance to the query. Then we will just use KNN search for short. Actually, KNN search is a very fundamental operation in a variety of applications, such as data cleaning, integration, web search, near duplication detection, bioinformatics, and etc. And the last question here is just why we just choose KNN rather than the threshold-based similarity search. Actually, it is very hard for people to specify the threshold in many cases. For instance, in search engine, people may just pay more attention for the results which rank first, say the top 5 ones. In such cases, if we use threshold-based search instead of KNN similarity search, it is difficult to find the results that are more attractive for users. Then we will introduce some related workers. There are already some existing approaches for threshold-based similarity search. One strive forward to extend them to support KNN search are shown as follows. Actually, this can be done by initializing the threshold as 1 and decreasing it by a fixed step at a time. For each threshold, we apply existing threshold-based approaches to obtain the similar records. This step is repeated until we obtain K results. However, this simple strategy is rather expensive as we need to execute multiple search operations during enumeration. Besides, as there is infinite numbers of thresholds, it is difficult to select a proper value for step. There are also some previous studies on the KNN similarity search with added distance constraint on string data. They adopt filter and verify frameworks and propose effective filtering technique to avoid redundant computing on the similar records. As verifying the addedness between two strings requires O(n) squared times, they devise complex filters to reduce the numbers of verification. However, as the verification time for similarity metric is just O(n), it is not proper to adopt such techniques to support our problem due to their heavy filter cost. To address these issues, we propose a transformation-based framework to efficiently support the KNN similarity search. To perform effective filtering, we transform all set records to representative vectors with fixed lengths. By carefully devising the transformation, we can guarantee that the representative vectors of similar records will be close to each other. Next, we use an R tree to index all the representative vectors. And we propose an efficient KNN search algorithms by leveraging the properties of R tree to prompt the similar records in batch. Next, we will talk about some details about the records transformation. Actually, we just group all tokens from the records in the dataset into M groups. For a record, we will have the numbers of tokens that belong to group I, which will be the values on its ith dimension in the representative vectors. Then we can define the transformation distance between two records by looking at the representative vectors. we will show that obtaining an optimal transformation is NP-complete in the full version of our paper. Therefore, we will also propose a greedy grouping algorithm to generate this transformation for all records. Then we will talk about the exact KNN algorithm. Actually, after obtaining all the transformed vector, we will index them into the R tree, which can naturally support both in-memory and on-disk settings. Then we will use a property of R tree to perform batch pruning when conducting the KNN similarity search. So specifically, given a query, we can estimate the upper bound of J-car similarity or also the lower bound of J-car distance between Q and R records in a node of R tree with the lower bound of the transformation distance. This is realized by considering the query node minimum transformation distance, which is shown in the pictures. So this distance seems very complex, but actually we can just consider it as the distance between the vectors of query and the nearest planes of the hyperrectangle of the node in R tree. Then the basic ideas of performing KNN search on a dataset is just shown as follows. We just maintain a priority queue R to keep the current k-promising results. And also we will let UB denote the largest J-car distance between the records in R to the query queue. Actually, UB is an upper bound of the J-car distance for KNN results to the query. That means we can prune an object if its J-car distance to the query is no smaller than UB. This object includes two types. One is node and the other is records. Actually, if the object is nodes, the J-car distances will become that the query node minimum transformation distance. Otherwise, that means if the distance is smaller than the UB, we will visit the child node or just simply add the records to the priority queue. In addition, we will also just adjust the visitor orders of the nodes to improve the overall performance. Next, we will also introduce some optimizations. The first is a multiple transformation. Actually, with a single transformation, we can only review a facet of the features in the set record. Therefore, the pruning power could be weakened due to loss of information. To address this problem, we can utilizing multiple independent transformations to excavate more information of data distribution. In a sense, the upper bound of J-car similarity will be the lowest one among the query node minimum transformation distance computed with multiple transformation, which will definitely be tighter. We also show that multiple transformations can be generated from the first transformation with the idea similar with greedy grouping algorithm. Next, we will talk about approximate KNN. So general idea is to estimate the KNN results by considering the distribution of data. Then we can find the KNN results according to the densities of data without traversing the index. This is realized by partitioning the whole dataset into several buckets and then incrementally search from the query point to identify the similar records. In this way, we can successfully find all the similar records within a cycle having a predefined radius, which might not be the exact KNN results, but will definitely make a good approximation. So buckets used in these processes can be decided smartly using the MBRs of existing R-tree index. Finally, we just conduct an extensive set of experiments on 3 real-world datasets, DBLP, PubMed, and Light Journal. We also compare with 2 existing methods called Flamingo and Tree, And in addition, one approaches extend from the state-of-art methods that is top case similarity, which is published in ICD 2009. Besides, we conduct experiments on the disk-based settings as well as approximate algorithm. The results show that our proposed methods outperform existing methods by up to an order of magnitude. The detailed results can be found in the full version of our paper, that is, a transformation-based framework for KNN similarity, which is published in TKDE 2019. So that's all for it. Thanks for your listening.